We live in a digital age. Computers are everywhere. They power our phones, cars, and even our homes. Ever wondered about the magic happening inside these machines? This is where understanding computer organization and architecture becomes crucial. It's like peeking under the hood of a car. We get to see the engine, the transmission, and all the parts working together. Similarly, computer organization and architecture reveal the inner workings of a computer system. This knowledge is key for anyone interested in computer science, software development, or just understanding the technology that shapes our world. Let's embark on this journey to demystify the fascinating world of computers. Often used interchangeably, computer architecture and computer organization are distinct concepts. Imagine building a house. The architecture refers to the design, the blueprint, the number of rooms, their layout. It's the grand vision, the overall plan, that dictates what the final structure will look like and how it will function. This is analogous to the computer's architecture. It defines the system's functionalities, the instruction set, and data representation. Just like a house blueprint, it outlines the essential components and their interactions, ensuring everything works harmoniously. Now, think about how the house is built, the construction process, the order of tasks, the tools used. This involves the practical steps, the materials, and the methods employed to bring the blueprint to life. This is akin to computer organization. It deals with the interconnection of components, their control signals, and how they collaborate to realize the architectural specifications. It's about the nitty-gritty details, the actual implementation of the design. In essence, architecture is the what, and organization is the how. The architecture provides the vision, while the organization ensures that vision is executed effectively. A robust understanding of both is essential to grasp the complete picture of a computer system. Without a clear architecture, the system lacks direction. Without proper organization, the architecture remains a mere concept, never fully realized. Together, they form the backbone of any successful computer system, ensuring both innovation and functionality. A computer system comprises several functional units, each playing a crucial role. These units work together seamlessly to ensure the system operates efficiently and effectively. Think of a computer as a well-coordinated team, where each member has a specific task, but collaborates to achieve a common goal. First, we have the brain, the Central Processing Unit, or CPU. This is the powerhouse of the computer, responsible for executing instructions and processing data. It performs arithmetic, logic, and control operations, directing data flow within the system. The CPU ensures that all tasks are carried out efficiently and accurately. Next is the memory, the storage unit. This is where the computer stores data and instructions that the CPU needs to access quickly. It holds data and instructions needed by the CPU, acting as a temporary storage area that the CPU can access rapidly. Imagine it as a massive library with shelves containing information. Just like a librarian retrieves books, the memory fetches data for the CPU. Then comes the input/output, or I/O unit, the communicator. This unit manages the exchange of data between the computer and external devices. It allows the computer to interact with the outside world, receiving data from devices like keyboards and displaying results on monitors. This interaction is crucial for user input and output. These units are interconnected, working in harmony to execute programs and perform tasks. The seamless integration of these components ensures the computer operates smoothly. Understanding their individual roles and collaborative functioning is fundamental to comprehending computer organization. Each unit, while performing its specific function, contributes to the overall efficiency and capability of the computer system. Data needs to travel between different parts of the computer. This is where buses come into play. Imagine a bustling highway system within the computer, facilitating data transfer. There are three main types of buses: address bus, data bus, and control bus. The address bus carries addresses of memory locations. Think of it as a postal service, delivering addresses to access specific data. The data bus is the highway where data travels between components, like trucks carrying goods to different destinations. The control bus carries control signals that manage and synchronize the operations of various units, acting like traffic signals, ensuring smooth data flow. The bus structure ensures seamless communication and coordination, making the computer a well-oiled machine. A computer program is essentially a set of instructions. But how does the CPU execute these instructions in the right order? This is where instruction sequencing comes in. The CPU follows a fetch-decode-execute cycle. First, fetch. The CPU fetches the next instruction from memory. Then, decode. The fetched instruction is decoded, understanding the operation to be performed. Finally, execute. The CPU executes the decoded instruction. This cycle repeats, ensuring instructions are executed sequentially, much like a conductor leading an orchestra, ensuring each instrument plays its part at the right time. When accessing data in memory, the CPU needs the correct address. This is accomplished through various addressing modes. Think of trying to find a specific book in a library. You could go directly to its shelf, which is direct addressing, or you could follow a series of clues leading to its location, which is indirect addressing. Similarly, different addressing modes offer flexibility in how the CPU accesses data. For example, immediate addressing uses the operand itself as the value, while register addressing uses the value stored in a CPU register. Understanding these modes is essential for efficient programming and memory management. There are two primary architectural philosophies: RISC, which stands for Reduced Instruction Set Computing, and CSC, which stands for Complex Instruction Set Computing. Imagine RISC as a minimalist approach. It uses a smaller set of simple instructions, each executed quickly. CISC, on the other hand, is like a comprehensive toolkit with a wider variety of complex instructions. Both have their strengths and weaknesses. RISC architectures excel in speed and efficiency for simpler tasks, while CISC architectures are well suited for complex operations with fewer instructions. The choice depends on the specific application and design goals. This module provided a foundational understanding of computer organization and architecture. We began by examining the basic components that make up a computer system, such as the motherboard, CPU, memory units, and various input/output devices. We explored the difference between the two, understanding how each component interacts with others to perform complex tasks. We also looked at how different computer systems are designed to meet specific needs, from personal computers to large-scale servers. We delved into the roles of functional units, such as the arithmetic logic unit, ALU, control unit, and memory unit, and how they work together to process information. This included a detailed look at how the CPU executes instructions and manages data flow. We learned how data travels within the system, from input devices through the CPU and memory, and finally to output devices. This journey of data is crucial for understanding how computers perform tasks efficiently. We examined how instructions are executed, breaking down the process into fetch, decode, and execute cycles. This helped us understand the step-by-step operations that occur within the CPU. We also explored how addressing modes provide flexibility in data access, allowing the CPU to efficiently retrieve and manipulate data stored in various memory locations. Finally, we touched upon the contrasting philosophies of RISC and CISC architectures. We compared their design principles, performance characteristics, and how they influence modern computing. This knowledge is invaluable for anyone seeking to unravel the complexities of computer systems. It provides a solid foundation for further study and practical application in the field of computer science. Whether you're a budding programmer or a tech enthusiast, understanding these fundamental concepts is a stepping stone to navigating the fascinating world of computers. It equips you with the skills needed to innovate and solve real-world problems. Understanding these principles also helps in making informed decisions about hardware and software, optimizing system performance, and staying updated with technological advancements. Remember, just like understanding the building blocks is crucial for constructing magnificent structures, comprehending the intricacies of computer organization and architecture is essential for creating efficient and powerful digital systems. Comprehending computer organization and architecture opens up a world of possibilities in the digital realm. It lays the groundwork for innovation, enabling us to build smarter, faster, and more reliable systems that drive the future of technology.